Welcome to today's Research Pays Off. I'm now going to hand it over to our speaker, Dr. Imad Abdallah, Director of the Center for Transportation Infrastructure Systems and Associate Professor in the Department of Civil Engineering at the University of Texas, El Paso.
Good morning.
Welcome. Good
Can
morning.
you guys hear me?
Yes.
Oh, okay. Good morning, everyone. Thanks for allowing me to present today. I'm honored. I put a presentation together. I thought I'll give you a little bit of some of the efforts we're doing at UTEP in terms of characterizing aggregates and asphalt mixtures, frictional performance. I'm going to focus a little bit more on asphalt mixtures. It's just I have over 80 slides, and I didn't have space to put more in the hour that I have. So my name is Imad Abdallah. I've been here at UTEP for over 30 years. The work that I'm presenting today was mainly done by our Ph.D. student, Sandeep Reddy, who's on the slide, and several other students that worked with him. And my partner on this project is Dr. Sohail Nazarian. Okay, I just have a disclaimer here. I'm not going to read it word for word. Just give 30 seconds to go over it. Okay. So I have a small outline here to go through. I have a few slides for the background to kind of go over what I'm going to discuss, a little bit background on why we did this effort, this work in terms of friction, and a review of the friction deterioration curve that I'm going to use a lot throughout my slides. So I figured I'll go over that to see for in some cases who have not used it, who have not seen how it works, just to get a feel of what the curve looks like and how we use it. And then we're going to go into a little bit on the aggregate quality, frictional performance, and then the hot mix as well. Go over some of the work that we have done and some of the new efforts that we've been going through right now, and future work. So a little flavor of what we have done, what we're doing, and what we're going to do. Okay, some of the background. We know that we understand the impact of fine aggregate on friction performance. We wanted to do the study to be able to quantify that, to understand how it works. One of the things we know that we've done a lot of work in terms of rutting in the past when we do mixed designs. We recently have been doing a lot of efforts in cracking and what we call the balance mix, to sort of balance it in terms of rutting and cracking. And we thought, hey, the third leg of the wheel is the skid resistance. We would like to look into that and see, so that we have all the three parts of the performance when we're developing a pavement or when we're designing a pavement. So we spent some efforts on understanding how skid resistance work. I'm probably going to mention a little bit few using the word skid and more on friction, because that's the focus that I have in the presentation, and where we started out in our research. We want to understand friction first, and then be able to correlate it to skid in the field. At the end of the day, our goal is to come up with a guideline that will allow us to incorporate skid resistance into any type of mixed design. Okay, and I kind of mentioned that earlier. Skid and friction, we use terms interchangeably. I'll probably focus more on the word friction, but we know that in terms of an asphalt mixture, 95% of the mixture is composed of aggregates. So we really need to understand how the aggregates impact friction. That's very crucial. And in the mixed design, if you look at after you design the road, after a couple of months, you go out there and the binder has worn off, right? So the focus is, how does the aggregate properties and the asphalt mixture properties impact friction? And we have a detailed investigation that I'm going to go through to show you some of the work that we have done. Okay, I put this slide on purpose because I have a lot of the results and the work that I'm going to show you has to do with how we measure friction. We use these two devices right here. On my left, I have the dynamic friction test device, which is what we use to measure the friction properties of the aggregate. Basically, it's a mobile device. As you see, you can use it both in the lab and the field. Short term, you're going to hear me say a lot, is the DFT. It shows you the pictures of the top of it. It's handheld. It's about 40 pounds, 50 pounds. And when you're ready to test it, you place that device on whatever area you're looking to test, and you can see the circular plate at the bottom that allows you to test the friction. Basically, it ramps up, and I'll show you an example of that in the presentation. And it breaks, and it kind of measures the friction property of whatever surface you're looking at. On the right-hand side, we use the 3D wheel polishing device to polish whatever we're measuring. In this case, there's an example here of an aggregate sample that we use to polish. So we slide that sample into the jig that you see here, the 3-wheel polishing device, and you see those 3 wheels there, it cycles to the number of passes that we want. Then we pull it out and use that DFT on top of that sample to measure the friction properties. So what do we do with that? The way it works is we're able to, and this is a picture of part of the lab that we have here. You're able to measure the friction on the aggregate and on the asphalt side, and I'll go over each in detail. On the aggregate side, you set up your aggregate ring. This it takes about an hour to set up the ring. You have to be, very careful. Make sure you set up a tight ring, and you're able to measure the properties. And in this case, we want to see the frictional properties of the device. You set up the ring, and you use the TWP to traffic it. And then again, as I mentioned earlier, the DFT to quantify the friction value. How you do that is you develop a curve. On the top right here, you see I have a graph that says friction value versus polishing cycles. It's a cartoon illustration of what we're looking at. But basically, we generate this curve by first generating the points. So before you start any trafficking, we measure the properties initial friction value. That would be at polishing cycle 0. And then as you polish it, you start developing these dots here, and then it sort of behaves in a sort of a power-shaped curve. You're able to fit different types of curves through this data. If they're very well behaved, and you can quantify the curve by any different process, and this allows you to sort of be able to find the friction value at any polishing cycle. We have, based on research and some of the background that we have done, we go up to 100,000 cycles. That's enough. You can see that in most cases, you start getting a flat line right here, and that's kind of enough to kind of give you what the terminal friction value. One of the things that we are interested in this work is the terminal friction value, which is what I have here highlighted. So we assume that at 100K, we use that as our terminal friction value to compare different types of aggregates. And we've been doing this work for several aggregates over the years. We have, I think, over probably 80 to 90 aggregates that we have quantified up to this point. So this test here takes a while. I think it takes over, just on average, over 40 hours. It's a very time-consuming test because you're going up to 100,000 cycles. That's 300 passes, right? So the wheel passes. Okay. The same thing we do with the asphalt ring. And what we decide to do here, there's several ways of developing the asphalt setup. A lot of agencies and researchers use slabs. We elected to use the SuperPave gyratory compactor sample because we have a setup that you could use. You can core the samples from the field, from the lab. We can control the air voids. We know what they are. We don't have to worry about that when we're compacting a slab. So we have more control over the SuperPave sample, and that's what we start following. And we have a setup, and like I said, it allows us to set them up the same way cores that we get from the field and the lab, and so we can compare the two. The process works the same way. You set up your rings, Here it takes about 7 cores to be able, if you're getting samples from the field or in the lab, seven pair samples to set up this ring, and you use it the same way. In this case, we go a little bit further than 100,000 cycles. When we started out the research, we used to go to 300 cycles, 300,000 cycles, and it was a little bit too excessive. We met with a couple of our research partners, and we decided, you know what, 150 sort of is a good spot to quantify what the terminal friction value. So the interest here we started is what would be the terminal friction value, because we want to know at the end of the day when it starts, having issues in terms of friction. But we do develop the entire curve. So we start off at the beginning when the mix is fresh, without any traffic. And then we develop the curve. And the two curves behave very similarly, fit a power curve through these data or similar type curve to quantify the behavior of the two parameters, the polishing cycles and friction value. Okay, I did this just for the benefit of, for those who haven't used this before. So the first time we do the test, here's the devices. And let's say we're trying to polish a ring that we have in here. The first time we do is we test it with the DFT. That's at 0.0. And then we start tracking it. And this is an example of how, if you can hear I don't know if you can hear the sound, but it's ramping up and then it's going to break. So once it breaks, we get the DFT value, and then we're able to plot the first point, and then we traffic it. And so we slide the slab into the cage there, and then we start trafficking it, as you can see over here. So we're trafficking it, and then we go at different cycles. So the first one would be at 500 cycles, and you can see the point is pretty close to here, because this is on a large scale. And we continue the process. We measure the DFT, we put it in and get the more cycles. So as we develop the curve and as we go further cycles, this is where it takes longer. So now we're at 50,000 cycles, and we keep the process all the way to 150 cycles. So you can see the pattern that we do, and you can see how well behaved. This is the real data. Once we have this data, we're able to fit a curve through it if we wanted to quantify it in terms of curve. If we're just interested in the terminal friction value, then we go ahead and report this the value here at 150,000. So that shows you fitting that curve through it. And so that's what we use in most of our work that we do, that I'm going to show you today. So I mentioned earlier that I'm going to talk a little bit about the aggregate and some about the asphalt. I'm going to focus a lot more on the asphalt just because of the time constraints. I'll be happy if you guys have any questions on the aggregate. We can discuss it at any other time. We have lots of data and information about it. But this is what a typical ring looks like. And we use aggregate larger than I think the number of 3/8. Whatever is retained on 3/8 to set up this ring. And you can see here, it being trafficked, and then using the DFT and developing the curves. I have here an approximation. This takes 40 hours to run this test. Okay, what do we use this for? We kind of use this for to kind of let us know, how good the quality of the aggregate that's going to be used. First of all, do you want to use this aggregate in the mix? Is this an aggregate so you can use it as a classifier into your specifications if that's what you want? Another way you could use it is when you're developing a mix design and you're blending different types of aggregates. You can also use this here to kind of see what would be more or less on average your final friction value based on the aggregates. As I said, in terms of long term, the binder doesn't play an important part in the friction. It's mainly on the quality of the aggregates. So On the asphalt side, well, definitely we need, this is important here because that's what we're looking at. This is a setup. I kind of showed it briefly just to repeat the process. We set up these super pave samples into a mold, and then we traffic them and then develop the curve here. This takes about 50 hours from setting up and running the test. So it's both are sort of time-consuming tests because we're looking at the number of passes. The DFT alone, when you're measuring the friction, is a very quick test. It's about a minute or so, whether you're in the field or you're in the lab. The one that takes, of course, time is trafficking sample. So I'm going to jump straight to the asphalt part of it. Here, one of the things we did is we wanted to look at the impact of the asphalt parameters on the friction performance. Does the binder, the percent of binder, varying the percent of binder, does that impact the binder grade? Air voids, is that something that we need to worry about when we're looking at the performance? Aggregate gradation, asphalt gradation, and then the aggregate quality. So we looked at all 6 parameters in terms of the friction performance, and we set up a very controlled experiment to do that. Before I get into the experiment, I just want to show you how I'm going to present the results. So for each of those parameters, we vary one of those mixed properties at a time, and we run the test. So in this case, we're varying it in 4 conditions. This is different types of mixes, and we collect the data, and then we end up looking at the terminal friction value. As you notice here, this is the time. I have this graph. This is when we used to go all the way to 300,000 cycles. Right now, recently, we are stopping at 150. So this is an old slide. Sorry about that, but it's the same concept. Since we assume that this is the terminal friction value, this is what we look at, and we compare and see if there's much differences by changing the mix type. So at each of those parameters that I just mentioned previously here, the binder percentage, grade, air voids, and the rest, we're going to do the same thing. And for those varied parameters, we're going to plot them in a bar graph just to show comparison of what the friction value is, and see if there's an impact there. So how did we do this? So to control the experiment and to look at the impact of these mixture parameters, we got a typical mix that we use here in El Paso. We got that mix, and we said, you know what, this is what the typical mix looks like, but we are going to control this mix. We're going to make sure that it's all from the same source of aggregates. So we switched some of these bins out and combined them, so we make sure that it's all limestone. We're using one source of aggregate, and then we mixed that together, and we received that mix into we use the super pave mix gradation, and we seed it into, as you can see here, into each bin size, and that's what we use to control. So now we know we're using completely 100% limestone, following a mix design that we have a super pave mix, and then now we can vary those parameters and see if there's any impact. So we wanted to make sure we use one source of aggregate so we can control the experiments. And for that, we start looking at the different parameters that I'm going to show you here. So for the first one we looked at is the binder percentage. Sorry for this animation. It's going. Sorry about that. The animation is not. Anyway, just to show you. So we looked at the binder percentage first, and this is the result from that. So we looked at the terminal friction values that you see over here. And you can see that there's not much change across, going from 4.1% to 7.1%. We looked at different binder percentages. The impact is not that much if you look across the range that we have. So we know that in terms of terminal friction value, the binder is not playing an important part. The second one was the binder grade. Sorry about the order of the graphs. I got my animation mixed up here. The second one, the result is the binder grade. So we looked at typical grades that we use here locally, PG 6422, PG 1722, and PG 7622. Again, very similar trend in the results. There wasn't much impact here. I got to go through this process each time. Sorry about that. So the other one is we looked at the air voids. So we looked at two extreme. We looked at 7% air voids, 3% air voids. And in terms of air voids, it might play a huge part in terms of rutting and cracking, but in terms of friction, there wasn't much difference. And that's why you're going to see a lot of agencies, they compact when they're looking at the friction performance. They could use a slab or coarse, so you can go either way. The next parameter we looked at is the aggregate gradation, and we went 60-40 in terms of passing retainer number 4 and passing number 4. We went 50-50 and then 40-60 just to see if there's much impact on the gradation. Again, all of this was done with one source of aggregate, limestone, and there wasn't much, again, impact here. The last one we did was the asphalt gradation, and also much change. So all these properties that seem to affect highly when you're designing rutting and cracking, these 5 parameters play a very important part in that. It wasn't as impactful on the friction performance compared to this last parameter that I'm going to show you right now, the aggregate quality. So for the aggregate quality, we went with the experiment like this. We went with a mix 1, let's call it, with 100% limestone. That's the control gradation that we used. And then we substituted the entire gradation, aggregates, following the same gradation with 100% sandstone. So we know sandstone is much more superior aggregate quality than limestone. And we did mix 1 with limestone, and then mix 6 with sandstone. And I'm going to show you this based on these 3 fractions of C sizes. Group 1 would be retained, everything above retainer number 4, which we're calling the coarse side of the gradation. And then on the bottom side, passing number 30, which is the fines. And then we came up with this middle portion here, which is the coarse fine. So this is what is passing number 4, retained on number 30. So we broke it up into these 3 stages first to look at how the quality of the aggregate is impacted. So you can see here at 100% limestone, we were getting 0.25, but at 100% sandstone, the value is 0.4. So there was a big jump between 0.25 and 0.4 here. So these are the 2 extreme values. And then we start playing with the portions of the gradation here and mixing the quality between a sandstone and limestone to see where does it impact, where does the quality of the aggregate becomes important. So we went with mix 2 and mix 5. And mix 2 was, we took the coarse side of it and we put 50% sandstone. The rest of it we kept as limestone. And then for mix 5, everything that passed number 4, we switched to sandstone. And then so we ran that test too, and you can see here, in this case, there was a little bit of improvements, but the big jump and closer to what 0.4 is, this is the goal that we want to reach, right? And we wanted to see which one gets us closer to 0.4. You can see 0.37 is going, everything passing number 4. When we use sandstone, we were able to achieve 0.37 in terms of the DFT value at 300,000 cycles. And then so we said, okay, well, now we know we need to focus on this area right here. Let's break these 2 up and see which one is the one that's controlling. So we went with the mix 3 and mix 4. We kept the limestone the same. And then here you can see we switched, and we had to keep with the controlled gradation. And that's why you see the different percentages here. So we went with sandstone here, 36%, between what we call coarse fines. And then in terms of the passing number 30, You see the limestone here where we varied it and we put sandstone. So looking at these two results here, is you can start seeing that the sandstone is, and this middle portion of the gradation, sort of contributes to most of what you get here with the 0.4. So looking at mix number 4, for instance, you have most of it, the coarse side and the fine side is made out of limestone, but the coarse fines, which is the middle portion of that gradation, is what seems to impact the most and give you a much closer value to where if you're using 100% good quality aggregate. Okay, so and then we don't have it on these slides, but we kind of went a little bit further and refined the impact of, there's several seeds between passing number 4 and retained on number 30. I'll show you a little bit of that in a few. But we kind of narrow it down a little bit further where exactly the most impact is. But to illustrate in this experiment is that the quality of the aggregate is very important in terms of the terminal friction value. And if you put good quality aggregate in what we're saying around the coarse fines and more of it there, you're going to, improve your friction performance. So this is a slide that my student did, and I thought it was a very clever way of illustrating the concept. He took sticky notes. So this orange or yellow sticky note that you see here, he took a sticky note and he put the 10 grams of the aggregate from each teeth size. Just to illustrate the point that we're trying to show is if you're looking at the number 4 seed size, you can only get one aggregate right here, and this is the area that it covers in terms of a sticky note. And then as we move down the gradation, you can see here there's 2 aggregates, and we kind of looked at the weight, make sure the weight is 10 grams for all of these that you see here. And as you increase this, you can start seeing that as you go further down, which is obvious to all of us, is you get more surface area. It's covering more surface area. And in terms of number 8, you can see it's starting to cover more of that sticky note. 16, you're almost getting full coverage. And then number 30, you have 2 of them. As you go finer, you get more area covering. So the concept that we're trying to show here is that you need to have, control the friction. You need to show, and on the surface, you need to have a surface area to be able to control the friction. And the more surface area you have, the more you can control the friction. So these large size aggregates, they're important in terms of friction, but there's not enough of them to control on the surface to control, because you don't get as much as you would get maybe in the coarse fines in this middle portion. And we know that, if you think of it, we're not going to get any performance because this after number 30, the fine particles are too small to be able to impact friction. And if you look at the road, you don't see these wear off with the binder right away at the early stage of the road. So you don't see much impact on the surface from the fines portion. So what we believe, and we've tried so many aggregates and mixes for the last 5 years. We've been working on this maybe for 6 years right now, 5-6 years, and we can consistently see that in this middle portion of the curve, you kind of get the balance of both. You're going to get still a good size aggregate and covering enough surface area to impact friction. So that's why we believe somewhere in this middle portion of the gradation, looking at this, if we're looking at a typical gradation right here, somewhere in this middle portion of the gradation is where the impact of friction is. And if you put a better quality aggregate there, you're going to get better performance. Okay. Now that we have done that, I'm showing you some of the new efforts that we have been looking at with what we have done. How am I doing on time? Halfway. Very good. Okay, thank you. So I divided this up into, again, the aggregate side and the asphalt side. I'm going to go over a little bit what we have, some of the work we're doing on the aggregate side first, and then I'll talk about the asphalt. So one of the issues we had here is this test is very time consuming. Is there a way to reduce the number of hours. So we looked at several options here. So the way it works, just to go over it really quick, you have your stockpile, you get your for your aggregate, you sieve it, you get retained number of 3/8, and you build your molds, and then you run your test, and it takes 40 hours to generate this curve. Well, can we use this graph here to use the trend line, because we know it's very well behaved, to maybe predict the terminal friction value right here instead of having to test all the way through? That was one of the exercises that we did. And the answer is yes, we can. We tried many ways. I'm just going to show you an example or two. We said we're going to quantify this curve by any type of function, similar to a power function. And we're going to look at measuring, for example, at 0, 5, and 25,000 cycles, and see how we can predict this curve. So we ran the whole curve, but we would use these two to see if we can predict this terminal value. And you can see here the results. The red is the measured, and then the predicted, we use the power function. You can even improve this by using other functions. And you can see they're pretty decent results in terms of getting the friction value. You can see the difference between the two is in the green right here. And we looked at sources all the way from limestone to gravel, to granite, to sandstone. And another exercise we did, so we tried different combinations, but we wanted to see which one is the most relevant. So we kind of simplified the equation, not to go through the math of this or anything like that, but we looked at, if we're looking at this curve right here, we use the power function, we use the beta function right here, and we said, okay, if we can quantify it and normalize our DFT to the maximum value, so we would normalize it to 1, take this raw data here and normalize it to start from 1. We're able to eliminate the alpha parameter or the A parameter here and just focus on the beta. So you have the beta parameter here, and that's one parameter we can worry about. Let's see if we can predict the terminal friction value. And maybe we can use that beta as a quantifier. So we did that. This is an exercise here. We only used at 0 and 50,000 cycles. And you can see here we were able to predict at 100,000 cycle with pretty good accuracy. This is the error bar or error lines is plus or minus 15%, and most of the data is well within that. So, and you can see the equation, the R squared, pretty good. I think we had about 47 sources of aggregate or somewhere like that in that sense. So that gave us an indication this is something very feasible. As we collect more aggregate, we can reinforce this equation and get something more reliable to use. But we don't even need to go all the way to 40 hours. We were able to reduce it to at least 15 hours, the test. So that's some of the work that we did. Another area that we worked on was, can we eliminate using the TWP complete, this test completely? And one of the things we were looking at is looking at the mineralogy. So we looked at angularity, texture, and then we looked at the mineralogy, and this was the one that was most important right here. I'm going to show you a little flavor of that. So we have an XRF. It's a portable XRF. Can we take this aggregate and be able to get the elemental components of this XRF, of the aggregate using the XRF? And can we relate that to the curve? So we have already developed these curves for many aggregates. And we went back and started measuring the XRF and getting the elemental properties of them. The good thing about this test, if you're familiar with it, it's about a few minutes. We just said approximately half an hour, but it literally takes about a minute or two to test one aggregate at a time. You can do multiple aggregates. We have refined this since then. But this is what it looks like. So for each aggregate, you're going to get the elemental properties. This is the elements that it gives you from the XRF. And you look at the ones that are most dominant, and we have them highlighted right here. We collected this data for several sources of aggregates from limestone, again, gravel, dolomite, rhyolites, granite, and so forth. And you can see here, we did, I think, we repeated it 3 times just to see the variability, how much variation you have, how much is the coefficient of variation or the standard deviation to see. It's very, very reasonable. And we focused on these elements right here. I think there's 7 of them. We focused on these elements and we said, okay, can we take this and do a neural network model or any type of AI model or even a regression? We had 26 sources of aggregate. We looked at a artificial neural network in this case, and we started predicting the curve. So in this case, we're not only predicting the terminal, but we decided that we want to predict the entire curve. So we're predicting the friction value at 0, 5, 25, 50, 75, and 100,000 cycles. And you can see we use the training set and the testing set if you're familiar with ANN model. Most of them are much higher than 0.8 in terms of R squared. So it was very reasonable. Again, we only started with 26 sources, but we have been ramping it up to get, we have over 80 sources to improve our model with that. So again, as I mentioned, you have very good results. Our R squared is larger than 0.8. The one that's most of interest would be the 100,000 cycles, and you can see very good results. But again, you can quantify the entire curve. This is some of the comparison of from the testing set that we had, so you can compare the 2 curves, and you can see very well, pretty decently behaved if you look at the data for different types of aggregates. And I'm showing you the raw data without fitting the curve through it. This is actual raw data at each point that we use the neural network model. Now, the advantage of this is if you want to rely on that, you don't need to look at running this test at 40 hours anymore. A few minutes and you have your results. So huge advantage with this process. We have a couple of papers out there that we're more than glad to share. You could look up to kind of go over some of the work that we have done. So this was a flavor of some of the aggregate work that we have done in the past. We are doing more of it. We have refined our XRF testing to give us more accurate results. And now I'm going to go over, have a little bit of time left. I would like to go over the asphalt side. Same thing we did. We said, okay, what does it take to reduce this 50 hours? We took the same approach. So I'm going to go a little faster here because it's the same process. You have a mixed design. You have different sources of aggregates. We kind of can look at it and say, okay, how can we use the aggregates data to predict the terminal friction value in the mix? And how can we reduce this to go less than 40 hours? How can we accelerate this process? So one of the ideas that was used, not us, but was used by the DOT was a blended DFT. They would take the aggregates, and based on the friction value of the aggregate, they would do some type of a weighted average and sort of give you an idea of what the blended DFT value would be. And that kind of helps in your mix design. So we wanted to take that process and see if we can improve on that. And we looked at a couple of ways to do that. I'll go through that right now. So this is the traditional way I showed you earlier, right? You measure it. It takes 50 hours to do, but you go through this process. So, and you develop this curve. This is the traditional measurement that takes 50 hours to do, and you have the curve that quantifies the mix in terms of friction. Another way we did is sort of what we did in the aggregate, is use the initial values to predict at 150K. And we got very well behaved results, and I'll show you in a minute. So we used a similar approach that we use for the aggregate. This is a lot faster. We are able to recut our time to just running it up to this point instead of all the way. Another one was we said we want to look at is the modified blending DFT, is where, where I showed you earlier that the middle portion of the gradation is the one that controls the quality, the friction value. So if you have a good quality aggregate and you focus it on that middle portion of the gradation, you're going to get good friction value. So we use that concept, and we're still finalizing this. It's going to be coming out soon. Who's going to be called Dr. Sandeep. Really soon is going to be the one who, we're publishing this. I think it should be in publication right now. And he's going to be defending his thesis this December on this work, but sort of modifying this a little bit and improving what was done in the past. And then we also used the blended value that was there originally to compare. So we have these processes. This is the measured. Let's say this is the controlled, and these are the different ways that we came up with. The one that says blended was already being used. This is what based on the weighted percentage. And so the power fit method and the modified blended is what we have been playing with to improve the performance. Okay, the required time for the first one, we said it was 50. If we do it this way and only get the first few cycles, we're dropping it down to 16 hours. So we're really cutting it maybe in third. And then, of course, if you go with the blended, you just have to use, for example, if you want the XRF, or if you want to run the aggregates, you already have that parameter at hand for each of the aggregates because you have quantified it for your state in terms of the curve. And you can use that terminal value to be able to blend or come up with a weighted average in terms of this to come up with what the mix terminal value would be. And then we do the modification based on what I said, that the coarse fines, very similar, improved on this equation right here to come up with that what would be that value to give the designer way if they want to look at friction when they're doing their mix design, they can do that. And this is very quick method eliminating, bypassing the TWP and DFT. So we have a total of 47 asphalt mixes. We broke it down into 33 mixes when we developed the power curve and the model, the weighted, not the weighted average, but the modified blending. And we kept 14 of them to show you as a testing to verify. So this is the measured data. This is if you were going to run the whole test that takes 50 hours. It's in red, and you can see we looked at different types of design. Mainly, there's a lot of super pave, the dense graded toms, and there's, I guess, one SMA. Just the different mixes that we had over here that we worked on locally. If you do the power fit, you can see across the samples, the 33 samples, you're getting very good fit, very similar results. If you include the predicted, that modified blending, it's in purple. I know it's a lot of data to look at, but you can still see it's very well behaved. In some cases, there's a little bit more error in it, but overall, very well. And then compared to the blending, this one gave you a little bit more error, but we just took something that was there and we improved on it. So all three ways, it's better than not having any, right? So just to give you some statistics, the power fit, 100% of the mixes were less than 0.05 in terms of absolute error. And if you look at the standard error of estimate, is 0.02. The blended was 45%. Of the data was less than 0.05, so about half. And then you can see that 0.06 is the standard error of estimate. The one that we looked at is the blended. Sorry for the error, the spell right here. But it went up to so we were able to improve this to 88%, which was pretty decent. And the standard error down to 0.03. Just to show you the testing data, what it looks like. I have it over here, the same color code, and you can see that, of course, the predicted power curve is probably the one that has the highest. You have 93% right here, But the modified blended is not that bad, right behind it at 86% of the data. And this is the result of the standard error of estimate. So very reasonable. I think we're heading in the right direction. And again, as we get more mixes, as we improve our curve fitting process, and we're able to get better, improve this more and more. This is another way to look at all 47 samples, and we just kind of wanted to show you in terms of an XY axis instead of the bar graph. Sometimes it's hard to see it, and we kind of put zones around them so you can kind of see how good the data is visually. This is for the power fit. This one was the modified blended, and this was the blended DFT. So this allows us now, if you want to do a mixed design, and one of the things you want to look at besides cracking and running, if you want to look at check, for example, skid is part of your process. Now you can use the power fit or any of those methods to go from, to help with your mixed design and to see how good your terminal friction value is, if that's what you need, instead of being required to go all 50 hours. But I wanted to kind of take you full circle. This is something that we're really happy about, and we've been working at it from both directions. That you can even go further than that. You can go with the elemental properties of the XRF coming from the XRF. So you have your stockpile. From there, we can tell you how good your mix is. I mean, we're a long way from that, but this is the idea. If we can go from here all the way to the mix design, I think we're onto something. Maybe we can bypass this test completely. As I said, we're a long way from that process, but that's the approach that we're heading to next, is going, that full circle. Excuse me. Some of the efforts that are ongoing right now is being able to compare. Sorry again about that. Let me bring all of this up. Is one of the things that we have is this device, this DFT, allows us to do the test in the lab and in the field. So we're happy about that. We're comparing lab and field data. The other advantage of this is you can core your samples from the field and bring them up into lab and then generate the curve. So as let's say you build a section, we know that the compaction in the field is different than compaction in the lab. You build your section, you can get those cores, and you can bring them in the lab. You can do them either on the wheel path or in between the wheel path, bring them to your lab and generate that curve and see how it behaves, and it gives you an idea of how good your friction value is. So that's one area we're looking at right now, and we're doing several sections. The other one that we're looking at is at the end of the day, when we're looking at data in the field, it's about skid. It's not about friction. That's what we measure in the field. That's what the DOTs measure. So a huge part of our effort right now is how can we relate all this friction information that we have to skid in the field. So that's another, I say future efforts, but we're working on it to make sure we kind of correlate, and we're starting to do that with the DOT. Another thing we're doing is we're looking for test sections. We would like to put some test sections out there based on the concept that I mentioned to you, where the course finds control. We would like to design, for example, if there's a section that's going to be put out there, you have your control. We can use that as a control section, and based on what that mix design, we would take it and improve it from what we think, improving the friction of it by looking at that coarse fine portion. So we might have to do a substitution of one of the bins, putting a little better quality aggregate, but only on that coarse fine portion of the curve, and show you how we can improve the friction. Or if you're using a really good quality aggregate to begin with, we can reduce the amount of because we know how expensive it is and how scarce it is, reduce it to where it's needed on your gradation to give you the same type of friction value without impacting. Again, when we do all this work that I'm showing you related to the field, we always check our cracking and running. So we make sure it doesn't impact cracking or running. But if there's any volunteers, any test sections out there, we would like to work with you guys and to see if there's things we can help with. We would working with a lot of suppliers, looking at their sources and helping them with that. But we one of the things we would love to do is demonstrate this concept and put some test sections out there. I think that was it. I would like to acknowledge TxDOT. Always, they have been a tremendous support for our research over the years, and continue to be our #1 supporter. So just want to acknowledge them and say thank you. And thanks to allow me to present today, and thanks to the team that have worked on this project. I hope we have some time for questions.
Thank you very much. I do have some questions in the chat, and I do see someone has their hand raised. We'll start with our raised hand first. Paul?
Hey, my hand shouldn't be raised.
Oh, there we go. There we go.
Go ahead.
Okay. All right. So Bernard said he complimented you on the testing factorials being very comprehensive. But he also said, however, did you perform a stepwise regression analysis or a Keiki information criteria to ascertain which parameters are significant?
Yeah, so
and I'm not sure if I pronounced that correctly.
yeah, I think if you're mentioning statistical wise, we did the t-test to check and see to make sure. I'm kind of just showing you briefly because of the time constraints, the results. But yeah, we made sure which of those, if we're talking about the impact of the binder of the mixed properties, yes, we looked at the t-test and made sure which one controlled and which one doesn't.
Okay. And then the next question from Nancy was, what was your control mix design? I think you may have addressed it after that, after it was put in the chat.
Yeah, we looked at a typical super pave mix design that we have here locally. That was when we did a very, very well controlled experiment, but we also looked at different mixes. I mentioned kind of towards the end that a lot of agencies have been asking us to look at their mixes. So we have done various mixes and looked at, and I have to say this, in the lab, we see exactly what I showed you, that force fines is controlling. We have not demonstrated that in the field, and that's one of the next thing we would like to do. We are working closely in the local area and the region here to identify some sections that we can do that. If there's any opportunities out there, we would love to, because it's one thing to do it in the lab, it's another thing to demonstrate it in the field. And we would love to see if it performs the same way as we perceive it in the lab, or as it's showing in the lab.
Thanks. All right, the next question from Greg is, what is your minimum friction value that you want to obtain?
Oh, that's a very, very good question, by the way. So one of the issues we have with this device is right now there is no standards. So in my lab, we have for example, what we say is 0.25. If you're running the same thing in your lab, you might be getting another value, not way off, but it might be, and you saw the scale from poor to really good friction is very narrow, right? Somewhere between 0.2 to 0.45 or 0.5 is sort of the range, So what is a good number and what is a bad number? We're working right now with several agencies to standardize this. Unfortunately, there's only one device, one manufacturer, and that's when you run into issues. The device is not when you purchase one and I purchase one, they're not both calibrated the same way. So we're putting some calibration standards in place. We're looking at making sure we all run the tests the same way. So we're trying to standardize this. Now that we have found out that this has a very good potential, we are looking at those standards, and that's when you can start saying, draw lines between what's the minimum, maximum, what's acceptable. I mean, I can tell you in our lab, if you get something around 0.2 in terms of the mix, that's pretty poor. You want to at least be above, around 0.3, for example. That's a very decent. But then again, that doesn't mean anything. And that's one of the issues we have. I hope other manufacturers, maybe this device, it's a really good device. It's a little pricey. It comes from comes from Japan. There's a waiting time on it, and it's like I said, it's pretty pricey. If we can get more of this going, more manufacturers, or if we use the same device, if we can standardize the testing and make sure we calibrate it, we all have the same standards, we will be able to set those criteria.
Deepak, I did see your hand raised.
Oh, thank you. I thought time is not there, so I thank you, Imad, for presentation. Hey, I have one quick question. It's not question, just information. The behavior looks like the interested area. We are looking 100K or 150K, right? Cycle.
Yes, sir.
So what if in the beginning, because it is reasonable, it happens so quick, right?
Yes.
So the interest is okay, what happens after 100K or 150K, right? And I see the behavior is a linear. So maybe it is possible to make life easy. Just like propagate that linear behavior towards y-axis.
Yes.
Again, make life easy. So instead of doing all those
complex
equation
curves,
in the
right?
early behavior doesn't make any sense to me. We are looking for the final, right?
Yes.
So it's just like a kind of, have you heard a calm clay model?
Yeah, you have a very, very good point. Yes.
Yeah, so maybe we can do that. Something K value on y-axis, and you can predict anything. So for me, it looks like it's really promising, but we can make it very simplified equation, the way I see it. Thank you.
No, that's a great point, and that's something we're looking at because you mentioned something at the beginning. You said 150 or 100K. Now that's where we, based on some of the work that was done before us and some of the work that we have done, we sort of stake those as terminal. We know it's not changing much at that level, so we said, oh, that's going to be a terminal. But what really is terminal? There's a lot of work done in the area, and you mentioned that, we're not interested at the beginning. At the beginning, it goes a little erratic. I'm sure you have seen some of that data because of the binder impact, and we're not looking at that in terms of friction. There's a lot of ways we can simplify that curve, and you're absolutely right. And so those are a lot of things that are out there to look at. This was our first attempt at it, and you can see that we're doing a lot more refinements and simplifying things. But first, we were trying to understand the behavior. So yeah, very, very good point. Thank you.
Thank you.
All right, we are at the top of the hour. We do have just a couple more questions in the chat. The first one I hope could be a quick answer is the DFT covered under an AASHTO standard?
Yes.
Okay. Bernard has another lengthy question here, so maybe I'll just send that to you in an email or something. And someone asked for your contact information, so I just included your office number and your email address in the chat.
Thank you. I should have had it up there. Thank you.
Yeah. So that is available to anyone still on the call if they want to grab that before they leave. Otherwise, people can contact me. So I want to respect everyone's time because we're a couple minutes over now. So thank you so much for joining us. We had a very large group today, and Dr. Abdallah, I appreciate your time as well. And thank you for joining us, and we hope to see you next month.
Thank you. Thank you for allowing me to present. I appreciate it.